Part 3 of Unit 9 is about colligative properties. Let's start by defining colligative properties. A colligative property is one that depends only on the number of solute particles present in the solution, not on the identity of the solute. So it doesn't matter what our dissolved solute is, a colligative property is changed based only on the number of solute particles present, not what it is. The three main colligative properties we're going to look at are vapor pressure lowering, boiling point elevation, and melting point depression. So the vapor pressure and melting point of solutions are going to be lowered with solutes added to them, and the boiling point is going to be raised. We'll start with vapor pressure. Because of solute to solvent intermolecular attraction, higher concentrations of non-volatile solutes make it harder for solvent to escape to the vapor phase. What that means is, if you dissolve a solute in a solution, the vapor pressure is going to be lower because the solvent particles will be attracted to the solute particles. So in our pure solvent solution, it's got a certain vapor pressure we've got 10 or 11 of the blue solvent molecules escaping into the gas phase. But if we add a solute to that, a lot of the blue solvent particles are attracted to the red solute because of intermolecular forces. So that's going to hold more of the solvent in the liquid phase. It's going to prevent more liquid molecules from escaping into the vapor phase. We have an equation to help us calculate the lowered vapor pressure. It's called Rasuls Law. Rasuls Law is the vapor pressure of a new solution is equal to the mole fraction of the solvent times the pure vapor pressure of that solvent. So you take the vapor pressure of the solvent before there was any solute added to it and multiply it by the mole fraction of that solvent to find the new vapor pressure. Remember that mole fraction is moles of solvent over moles of solute plus solvent, the total number of moles. That will give you your new vapor pressure for the solution. Freezing point and boiling points of solutions are altered when solutes are added to them. Freezing point is going to be lowered. Something will freeze at a lower temperature, and boiling point is going to be raised. A higher temperature is required to make something boil. And we've got two very similar equations to calculate these. For freezing point depression, delta T, the change in temperature, is equal to I, which we'll talk about in a second, times Kf times little m, molality. Our equation for boiling point is change in temperature is equal to I again times Kb times molality. So we know what molality is in a solution, moles of solute per kilogram of solvent. Kf and Kb are constants that should be given to you. Kf is the freezing point depression constant, Kb is the boiling point elevation constant. I is something called the Van Hoff factor, and it describes how many particles a solute dissolves into. So for all molecular or organic substances like CH4, it's not going to dissociate into ions when it's dissolved in water. So it would have a Van Hoff factor of 1. If we look at sodium chloride, when sodium chloride dissolves in water, it breaks up into two ions, a sodium ion and a chloride ion. So that would give sodium chloride a Van Hoff factor of 2. So I is describing the total number of ions that something will dissociate into. Magnesium chloride, MgCl2, that's going to dissociate into 1 magnesium ion and 2 chloride ions. So that's 3 ions total. So magnesium chloride would have a Van Hoff factor of 3. So for all molecular substances, Van Hoff factor is going to be 1. For all ionic solutes, you just need to figure out the total number of ions that it would dissociate into and plug that into your equation. So let's look at an example problem. let's say that we dissolve 1.5 moles of calcium chloride in 1 liter of water. And we need to find the new freezing temperature and boiling temperature of that water. Well, this table tells us what our Kb and Kf values are. We know that water normally boils at 100 degrees Celsius, so we're going to, after we add the calcium chloride, it'll boil at a temperature above that, and it freezes at 0 degrees Celsius. After we add the calcium chloride, it'll freeze at a temperature below that, so a negative Celsius temperature. We'll start with the freezing point depression. We know that delta T is equal to I Kf m. So let's start plugging things into our equation. I is our Van Hoff factor. This will dissociate into 1 calcium ion and 2 chloride ions for a total of 3 ions. Kf for water is 1.86 degrees Celsius divided by molality, so 3 times 1.86. And our molality for this is moles per kilogram. Well, we've got 1.5 moles, and the density of water is 1 gram per milliliter. So if we've got 1,000 milliliters in 1 liter, we have 1 kilogram. So it's actually 1.5 divided by 1, or just a 1.5 molality solution. So 3 times 1.86 times 1.5, that's going to be equal to 8.37. Sorry if my 8 went off the screen there. Again, that is not our new freezing temperature, because we know that it's freezing point depression. So this is delta T, the change in temperature. So our new freezing temperature for water is actually going to be negative 8.37 degrees. We had to subtract that from 0. Now let's look at that with the boiling point elevation. Same equation, almost. Delta T equals I Kb, because we're looking at boiling, times molality. Our Van Hoff factor is going to stay the same, because calcium chloride dissociates into 3 ions. Take a new value for Kb, it's 0.51 degrees Celsius divided by molality. And our molality even stays the same, 1.5 moles per 1 kilogram of solvent, so 1.5 molality. So 3 times 0.51 times 1.5 will give us our change in boiling point temperature, and that's equal to 2.30. Again, that's not our final answer, that's the change in temperature. So the boiling point is going to be raised by 2.3 degrees, or the new boiling point is going to be 102.3 degrees Celsius. So that's how the colligative properties equations work. Your question for this section: how many degrees will a boiling point of 500 grams of water change if 20 grams of lithium chloride are dissolved in it? You might need to look back at the page previous to this for the constants that you need for your equation.